Thank you very much, Clotilde, for the kind introduction, and I would like to thank the organizers, in particular Jörg, for organizing this whole series of events and this particular workshop and inviting me to come here and talk about interfaces, theoretical approaches that we take to understanding interfaces. As Clotilde mentioned, it's difficult, but difficult is exciting, so it's a great pleasure to be here. And of course, also, if there's anything that you would like to discuss throughout the presentation, please jump at me and come forward with your questions or concerns. Because what I'm going to talk about is, let's say, not all in my, let's say, direct comfort zone. It's the work that is done by PhD students, and they are working at the forefront of development. And so there are many aspects that I'm myself very excited about to talk about. I'm from Forschungszentrum Jülich. Forschungszentrum Jülich is part of the Helmholtz Association, and I will have a few more notes on that in a few minutes. Here's my outline. So I will talk about the analytical theory of electrochemical interfaces, so the approaches that we are taking, and then how we expand it to an approach in hierarchical modeling or in electrocatalysis that allows us to decipher electrocatalytic reactions. So I will talk a little bit about, let's say, the ingredients, the modules that we need to be able to do that. And then I will talk about electro-ionic coupling at supported nanoparticles, which makes direct use of this analytical theory to understand the synergy between the support material and the particle and how it's interacting with its surroundings, so the electrolyte solution. And then I will present the freshest results from a classical theory of electron-ion correlations. So within the Helmholtz Association, we have long-term programs funded for 7 years, and within these programs, there's a strong focus on energy technologies. And so here are the different foci that we are taking: battery energy storage, hydrogen for mobility, chemical energy storage with certain applied aspects that we are working towards, that we try to accomplish together. Helmholtz has in total about 50,000 employees working there. And in terms of its mission, it's somewhere between Max Planck, which has the privilege of doing very fundamental research, and Fraunhofer, which is doing applied research. So the mission of Helmholtz, or the research in Helmholtz, follows the mission of doing use-inspired fundamental research. So you see the uses here. The fundamental aspects that we are focusing on are materials related. So coming from electrocatalyst materials, ionic media, interfaces and electrodes, and then how it all works together when we get to the device level. Our contributions are in theory and computation, and so we try to develop approaches that integrate different theoretical models and simulation approaches that can be developed in theory and computation. And we try to bring in these elements of realism, so to move away from the model type interfaces, which have many challenges, of course, and are complex enough to study. And then we work towards model-based lifetime performance assessment. And so this is a direct contribution to the technology development. There's a lot of interest from companies that work in the space of developing electrochemical technologies, fuel cells, and more so recently electrolyzers, water electrolyzers, but also CO2 electrolysis is an important topic there. And then we devise methods and tools for a rapid exploration of the material space that make use of the developments in data analytics, artificial intelligence, and so on. What brought me directly, let's say, to this field of interfaces and to, let's say, being motivated to more deeply understand what happens at an interface was a challenge that we came across many years ago, probably more than 15 years ago. And so there was a type of electrode that was made for the oxygen reduction reaction in fuel cells. And this electrode was only consisting of platinum, and the porous platinum, nanoporous platinum, was filled with water. There was nothing else. There was no intrinsic electrolyte that these pores were filled with. Of course, then it turned out that these layers provided quite a good performance. They were outperforming any other type of catalyst layers, usually impregnated with ionomer that was providing a proton density and so on. And we talk about the oxygen reduction reaction, which is a reaction that consumes protons, so it needs protons. And if the situation is like this, it's totally not understandable why such a layer could perform well for the oxygen reduction reaction, because the oxygen reduction reaction is performed somewhere here. And if you follow textbook style electrochemistry, the charging relation of platinum should be in the range of a positive surface charge, where it would be a very hostile environment for protons. So there wouldn't be any protons there for a reaction that consumes protons. And so the performance should be more like this than like this. So this was kind of the, let's say, driving motivation for us. Yes, please. Sorry?
What is the pH?
Oh, the pH. Well, very good question. So after we did the modeling of this, so you don't know what the pH is, right? Okay, so you can, let's say you can go to the surface charge density. You can go to the surface charge density. It's only water. It's pure water. So you would expect the pH of neutral water. Unless, of course, there's an influence of the surface charging of the catalyst on the pH, on the local pH at the interface. And this is what I was referring to here, right? We have the platinum catalyst. The catalyst has a certain surface charge. And so it will create an environment, of course, where this surface charge must be balanced. And so that will tune, let's say, the pH in the vicinity of the surface. But my statement was that at this potential here, the surface should be hostile for protons. So there shouldn't be protons there. And it should be even less than neutral pH. Yes.
Sorry, just to follow up though, like, you know, when I think of 4R, it should be 1.23.
Yes, so we come from here. We come from here.
If you're down at like 0.920, it's a typical catalyst for a fuel cell. Even neutral.
It's what? Sorry?
It's a typical catalyst for a fuel cell.
Yes, yes.
But you're saying it's better than what you expect.
It's better because the pH wouldn't be, so the proton concentration would be much lower than we would need to get such a good performance. So simply based on electrochemical charging relation of platinum, we wouldn't expect it to be at this performance. We would expect it to be more like this. Okay? But it turns out the pH at the interface, so understanding local reaction environment, right? So the pH at the interface is not like 10 to minus 7, or so proton concentration is not like 10 to minus 7 or even smaller, but it's in the range of 10 to minus 3, 10 to minus 4 moles per liter. So it's quite a decent proton concentration after we developed a model for this, accounting for various properties of the interface. We can talk about it more later. So that was my motivation. So the interest in the local reaction environment. And so local reaction environment is something that establishes at an interface, and it has an impact on the kinetics of reactions. Some we want, oxygen reduction reaction, for instance. We want that reaction to pursue, so we want to have, let's say, protons at the interface. But for instance, for platinum dissolution, it's very bad to have protons there. So in general, it's important to know what this is. And it's not determined simply by interfacial properties. There are intrinsic materials properties that come into play. So what is the electronic structure of the catalyst? How is that affected by the support maybe? And also the, let's say, macroscopic phenomena like the transport of species, of oxygen to the reaction site and so on come into play. So it's basically merging the effects from two sides. And they come together at this interface and determine the local reaction environment. Now, if you get into the field of the electrocatalysis, of course, there are certain handles or knobs that are at the hands of the experimental electrochemist. So electrode potential could be controlled, pH, ion concentrations, and so on. Then the material scientist can make materials with many different morphologies, structures in different compositions, varieties, and so on. And they determine a range of different properties, from the intrinsic properties, interface properties, all the way to electrode properties and performance. What comes into play in this interfacial region, or in let's say, basically getting from this level here to this level, is the effects that are due to electrolyte, that are due to the electrode, and in particular the boundary region between electrolyte and electrode, where all of these things that you see here are happening. So electronic structure effects, solvent polarization effects, ordered solvent layers, some degree of ordering that might happen, and surface modification due to chemisorpted oxygen species, for instance, in the case of platinum. So what we need to understand all of this and to make this connection between these two rails at the bottom and at the top is an interface energy functional. And so, of course, this can be, in a way, obtained from simulations, or we can try to get to this interface energy functional with a theoretical approach. And so we started out with developing an approach specifically for the platinum electrode, but then this got more like developed its own dynamics. And so then other people got involved. I will show on the next slide who are the contributors to this. But basically, our objective is that we would like to describe the electronic conductor, the metal side, and the ionic conductor on an equal footing. So not neglect any of the degrees of freedom. On the metal side, we have electronic degrees of freedom. On the ionic conductor side, we have solvent and ionic degrees of freedom. All of these must be accounted for, in principle, at the highest level of theory available. Then we have to make the compromises that we cannot describe all of these degrees of freedom at the level of quantum mechanics. So there needs to be some element of a classical description in this. And such a very efficient framework for performing such calculations and treating these degrees of freedom on an equal footing was developed by the individuals that you see here. So Jun Wang was involved pretty early. So he started the development of models of approaches for the platinum surface that gave us the insight in what is the local pH at the surface. And then other individuals, Menke and Niels and Yufan and Tobias, got involved at later stages. And basically, this is an analytical framework. It doesn't use Kohn-Sham density functional theory. It uses orbital free because that's computationally more efficient. And there's a fully analytical formulation of the electronic energy contributions to the overall grand potential. And we treat electrolyte species at the level of statistical field theory, and it's grand canonical. And then pairwise interactions are, of course, accounted for because we don't want, let's say, water molecules, for instance, to penetrate into the metal region. So there needs to be a strong repulsive potential at the interface.
Just a clarification. So this is orbital free for
Yes.
a metal?
For a metal, yes. Yeah.
Not for water or anything?
No, no. The metal side is treated as an inhomogeneous electron gas with the orbital free density functional theory. And for the electrolyte side, we have statistical field theory, so a classical approach for the electrolyte side. So in principle, it's kind of a joint density function or similar to a joint density functional theory approach.
But then what happens at the interface, we don't know. I mean, at the microscopic level.
Well, we'll see. We'll see, okay? So in principle, we have a description for all the degrees of freedom in the system. We have a framework to describe what the electrons are doing, how they are distributed, and how they determine the potential inside of the metal phase. And we have a description for the electrolyte solution side. It's classical, but we'll see how far we can get with that. And then also we have, let's say, direct terms at the interface. And this is how this overall energy function looks like. So it's all analytical, as I mentioned. So this is the orbital free description of metal electrons, Thomas Fermi type. Short-range interactions between dipole molecules are accounted for. Coulombing interactions and cross-coupling terms at the interface are accounted for. So interactions between ions in solution, ions with electrons in the metal. There's configuration entropy and accessory energy and short-range metal solution interactions. And then we make this all grand canonical, so controlling the electrochemical potentials of the species involved. Now, variation principle can be used to obtain a closed set of the governing equations. And just as an example, this is a modified Poisson-Boltzmann equation that comes out of the wash if we apply the variation principle to this grand potential. And any other like distributions and equations that govern electron density distributions in the metal and so on, we all get it out of this.
So your
yes?
metal is just a gallium, or do you have some really individual atoms? I mean,
The metal, yes, it's individual atoms.
Okay, because in principle, so you're mainly interested in the screening, or so electronic screening.
No, that's right. But no, the atom, so the cores are explicitly located on lattice, and the electrons are swarming around. But we are using this orbital-free approach for those. And so here are some results. So we get the distributions, local distributions of potential seen here, huge variations inside of the metal. And then much smaller variations, of course, on the electrolyte side. So we zoom in here. This is at different electrode potentials applied. Here is the solvent polarization. Solvent polarization turns out to have a huge impact on the layer distributions of ions as we can see here. And you see overall, let's say, the expected trends for ion density. So if the potential is more negative, we see the enhancement of cation concentration. More positive, we see an enhancement of anion concentration. And there's also a specific or peculiar effect of the solvent that even, let's say, at the potentials where we would not expect it, there's an enhancement of anion concentration close to the surface. So this is kind of, let's say, in arbitrary resolution going to the surface because it's all continuum mathematics here, these distributions that we can obtain. And of course, no one has been there, so no one knows how these really look like. What we know is, let's say, the capacitive response of an interface. And so that has been calculated here at, for different electrode terminations. So crystalline configurations at the surface for different types of electrolytes and also for different electrolyte concentrations. So the, let's say, Chapman minimum is nicely reproduced, and then the maxima are reproduced, and also the flanks are quite well reproduced with this type of approach. So let's say this is kind of a foundation for other activities that then we are building upon. Now, and I know that Jun Wang was presenting in one of the previous workshops, and I assume that he has talked about this in some more detail and then taken off in different directions. So now coming to the topic of realism and complexity. So we need some kind of hierarchical modeling because local reaction environment is only, let's say, at the interface. We need to connect it with the macroscopic or the larger length scales so that, let's say, what happens at the interface can be connected with what is provided outside of an electrochemical system in terms of reactant concentrations, in terms of, let's say, ionic concentrations and so on, solvent composition. And so we need this hierarchical modeling. I will then talk about electro-ionic coupling and supported nanoparticles, and then about this part here, classical theory of electron-ion correlations. And not this one, but this would be also an interesting topic for another presentation maybe. So the role of ionomer in catalyst layers or at interface. So for the hierarchical modeling. So first of all, if you want to understand electrocatalytic reactions, there are multiple factors that need to be accounted for. Of course, there's thermodynamics, and it's well known, let's say, that activity might follow kind of a certain pattern due to adsorption energies, strength of adsorption energies of intermediates varying with the type of metal. And so there will be a sweet spot, an optimum in terms of activity, for the activity in terms of the binding of an intermediate. And then to the two sides, it will decrease. So this is, of course, the volcano curve that follows from Sabatier principle. So thermodynamics in basically condensed in a single descriptor, which of course is a huge oversimplification. We don't have to make this simplification if we combine this with multi-step kinetics and are able to calculate exactly reaction pathways, for instance, approaches that Jörg Neugebauer was talking about earlier. So then we can calculate what are these different energy levels. We can calculate maybe activation energies. And so we get a full picture here. And based on this, then there are, let's say, we can solve a microkinetic model, and we get an expression for the overall rate of a reaction. And I illustrate this for oxygen reduction reaction here. So this, the overall or net rate of the oxygen reduction reaction is shown here in the denominator. And so this is kind of a resistance to oxygen reduction reaction. And it is composed of various resistive terms. Now, these can be parameterized. That would need the DPFT type quantum mechanical calculations. And with the full parameterization, then we can obtain, or we can plot how each of these terms here varies with the electrode potential. And then we see that, let's say, with electrode potential decreasing from equilibrium, which would be somewhere here, going to higher and higher overpotentials for the oxygen reduction reaction, then different terms would dominate here. So first it is this term here, and then we would have a transition to this term here, which would be this one, and then ultimately at very high overpotentials it would only be one barrier that is remaining because other barriers have gone. Yes?
Can you tell us what the K's are?
Okay. So the capital K's are equilibrium constants. So, and it's 4, 1, 2, 3, 4, because there are 4 elementary steps of the oxygen reduction reaction. No, I didn't want to talk about it in detail. This is just an illustration, right, of what we can do with it. So if this is all fully parameterized and we solve this microkinetic mechanism, right, so 4 steps for the oxygen reduction reaction. And what's interesting about this is there's a small case, there's a capital case. The small case are related to activation energies, so they are kinetic constants. And the capital case are equilibrium constants, so they are related to Gibbs reaction energies. So it shows you, let's say, if the reaction is proceeding, for instance, at very small overpotentials for the red curve here, this would be dominating. You need to calculate the activation Gibbs energy for the first step, and for the step 2, 3, and 4, you only need reaction Gibbs energies.
So say what is P plus 1? You're saying everything is due to one, there's only one kinetic parameter?
These are the forward rates. K plus 1 is the forward rate for the first step of bringing an oxygen to the surface. So the oxygen molecule comes to the surface, is associated with a proton and an electron. Okay, forming OH. That is the first step. Okay, but as said, I didn't want to talk about this. I just wanted to illustrate this. Yeah.
Just want to ask, in the model right now, you have, do you take into account the potential dependence of the K?
The what? Sorry?
Potential dependence, because when you change...
Yes. This is, of course, this is why we see these different terms changing with potential, right? So the potential is explicitly accounted for. Yes.
Because that will change the environment, like the surface
well, that is not
coverage
accounted for.
effect.
That is not accounted for. So, of course, then, with this, we get a description where we can, in principle, resolve how the Tafel slope would vary with potential, as we get all of these different transitions here. And so just to demonstrate what the capabilities of these are, right? Okay. And then there's some agreement with the variations of Tafel slopes that has been seen in the literature, in various experimental studies, right? So we see these kind of transitions. Tafel slope is not a constant. And so the exchange current density of a reaction is not a constant. It is a hugely varying function with potential. Okay. So other factors come into play. So this you can do without accounting for local conditions. If we factor in local conditions, so we bring in this model of the EDL structure, the model that Jun Wang is developing further, and we combine it with approaches for mass transport, then we get a better representation of what happens at the interface, but we need more, let's say, theoretical tools or more equations in principle to handle this. So we need to modify Poisson and Planck theory. So an equation for the transport of ionic species. We need some description of the charging conditions of the local reaction environment at the electrochemical interface. So we need our double layer model that's here. So this is the relation between the free charge at the metal surface and the electrode potential. Okay, accounting for different layers that we have close to the surface, Helmholtz layer or inner Helmholtz plane, outer Helmholtz plane, Louis-Chapman, and so on. It can all be accounted for. Okay, there's a charging relation for this. And then we can apply this to reactions of interest. All of this together, right? The thermodynamics, the multi-step kinetics, this EDL structure model, and the mass transport. And so one of the analyses that was done by Jingwei, he was a student doing this, was focusing on formic acid oxidation, where peculiar dependence is seen on the pH. And so that dependence is shown here by the symbols. If you only account for intrinsic factors, only thermodynamics, and we solve this microkinetic model, but not accounting for anything that happens locally, we get a bell-shaped curve. If we now bring in the mass transport, so we couple this to the transport of species or via diffusion, via convection, and so on, we see it is developing a plateau. And that is already qualitatively in agreement with the experiment. If we now bring in this surface charging model, so local reaction environment, so closest proximity to the surface at the reaction plane, there's a variation of conditions, and we need to know what is the pH at this surface. We need to know what are the reactant concentrations and so on. If we bring that in, then we can match very well the experimental data. And so now this has been done also for other reactions. I've shown already the oxygen reduction reaction, oxygen evolution reaction. We see this variation of Tafel slope here, and the variation of the rate determining term corresponding to that. And here, as I was mentioning before, this variation of Tafel slope for the oxygen reduction reaction with potential also agrees with what had been seen in experimental studies. And so, in principle, so this sums up this part here. So there's the capability that, let's say, we can calculate or we can resolve what is the local reaction environment at the interface. And for this, we need these approaches for double layers, solving double layer models or simulations. If you combine it with microkinetic modeling and simulations of reaction pathways, then it is possible that these reactions can be deciphered. And deciphering for me means that we are able to describe how does the Tafel slope vary with potential? How does the effective exchange current density change with the potential? So that means that we are able to decipher such reactions. And that would be the prerequisite so that we can apply this to electrocatalyst selection and screening and to an optimal design of catalyst layers. Any question on this? Yes.
Hi, Michael.
Yeah.
So I really like your models. I mean, it's pretty impressive also the good agreement with the experiment.
Mm.
So what I'm really wondering about, because I was also involved in the QMMM model development with Kim and
Yes.
Kais, and we got a capacitance curve and it was qualitatively matching with the experiment, but not quantitatively. But now I see you get like such an excellent
Yes.
quantitative match, and I
Has to
know
be-
that in these models you still have a lot of parameters.
It has to be taken with a grain of salt, right? Of course, there are parameters involved, and we have to make sure the parameters are, for instance, the size of ions, right? So we have to make sure that these parameters are physically meaningful, and of course, there needs to be an independent check, right? Maybe with quantum mechanical simulations, what is really the solvation structure around an ion, right? So
Do you use consistent parameters
Yes.
for explaining all different results?
yes, there was one set of parameters. And the only property that was varied was the parameter that was shown in the legend, right? The concentration of ions and or the different type of electrolytes. So then it means if you use a different electrolyte, different ions, then we would have different ion sizes, for instance.
Sure.
Yeah. Okay. Yes.
And so to get those density fluctuations you showed at the beginning of your talk, like of the water density and the ion density, is that based on is that from like a classical density functional, or is that come out of Realism? Like what?
This
what
is
interaction
a
is this?
statistical approach for the statistical field theory applied to for the electrolyte. So it's nothing quantum mechanical.
Okay,
It's
so
purely-
you're basically solving for the density with some kind of excess functional.
Yes, that's right. Yeah.
Do you assume anything
Yeah.
on the shape of the surface, corrugation of the surface? Is that a
Yeah, sure. I mean, the surface
the effect
configuration,
of
the let's say of the metal that goes into the setup of the orbital-free DFT
yes.
part, right? So that's in there.
So
It's in there. Yes.
And do you observe any effect of the surface corrugation on that distribution?
Well, I couldn't show you that now, but certainly I think there will be effects. But I would have to dig that out. Yes.
Have you checked the transferability of the model to other metals like platinum?
Well, it wouldn't work for platinum.
Why?
It doesn't work for platinum because the orbital-free DFT approach is not well suited for metals like platinum.
Because it can-
That's why we apply this for silver and gold, right? Yes. Okay. Yeah. Maybe we can shift other questions on this part to later, and I will move on because I have more interesting things to talk about. At least from my perspective, I want to get to that. Okay. So we use this approach then to study the electro-ionic coupling at supported nanoparticles. And so this is basically one-to-one taking this density potential functional theory, orbital-free DFT for the metal, classical statistical mechanics for the electrolyte, and using it to describe actually a supported nanoparticle system. So we have a silver particle on a gold support. So these are the metals for which this approach, in our view, is well suited. Now, of course, there are various effects. There's electronic equilibration that happens. size and shape effects have been seen to exert, of course, a strong impact on electrocatalytic activity. Chemisorption, in principle, would need to be accounted for, but so we chose metals where this is not, let's say, such a big concern. There could be spillover effects. What is important is that, so we have three types of interfaces. Okay, so we have an interface between the particle and the support, so a metal-metal interface, and then we have two metal-electrolyte interfaces between the support and the electrolyte, and between the particle and the electrolyte. And then, what is important is we study equilibrium, let's say, distributions, equilibrium properties of this configuration. So we need equilibration simultaneously at all of these different interfaces, at all three interfaces simultaneously. Which means, so we have two parameters to play with. And so the two parameters are the potential of zero charge of this particle, of this nanoparticle, and the potential inside of this nanoparticle. First, using this DPFT approach, the stability of the silver on the gold was studied, and we see the stabilization at the distance of the surface of the silver particle from the gold of about 0.1 nanometers. And the binding energy per atom is in the range of 4 electron volts. Then we checked how, let's say, the work function is changing as we move from a fully uncovered gold surface to one that has more and more silver particles deposited on it, so the coverage is increasing and the work function must decrease, following, of course, the difference of the work functions of the silver and the gold. And here we checked the result of the DPFT, of this quantum mechanical classical approach with full DFT calculations. And we see trends are agreeing, and qualitatively, of course, there's a discrepancy. And now we study what is the charge density distribution in this configuration. And this has two elements. So it has the element of the electronic charge density distribution. The density is given here. So this is the departure in the contacted system from the, let's say, systems where the two components are separate. Okay, so this is how the electron density is changing. And there's also a density in the electrolyte. So the ion density, anion excess, cation excess. So blue regions meaning relative negative charge, and red regions positive charge. And this is the same for electrons and protons. What you see here, there's a kind of course, strong accumulation of charge at the interface between the particle and the support. Electron density strongly increased in this interfacial region. It's not a double layer, it's kind of a triple layer, indeed. And there's a little bit of charge. So not all the charge is concentrated directly at the interface. There's also a little bit at the particle surface, and a little bit is spilling over onto the support. But these charging effects are much more pronounced when we go to the nanoparticle, to the electrolyte environment. And there we see a strong charging. Now there's huge excess of positive charge on the, so depletion of electrons on the surface of the metal, of the silver nanoparticle, corresponding excess of electrons on the gold, and the matching distributions on the electrolyte side. Okay, much stronger effect because now we have the screening of charges by the electrolyte, so that increases the accumulation of charge. And so in principle, this is kind of an in-plane capacitor configuration. So in the plane, we have positive charge here, negative charge here, so it's kind of a capacitor configuration that we have there. Then we submitted a manuscript on this work. First, it only had these results for this DPFT type approach. Rivia was recommending we should also do explicit DFT simulations. So we did that using VASP. Same configuration, same setup, and we get, in principle, very good agreement, right? The different environments in vacuum and with the electrolyte, and also the amount of charge, of excess charge in the two cases for this configuration here. I think the agreement is not too bad there. So qualitatively and even maybe quantitatively, you can say there's good agreement that was achieved. And again, then there's a practical interest. And the practical interest motivating us is what impact will it have on, let's say, effective reactivity? And so if you bring particles closer together, so here, this is half a cell, right? So the next cell would start here. So we have a particle in about 4 angstrom separation, and here the separation is much larger. If the electrolyte is more concentrated, this will not have a big effect, because the double layers around these particles will be very small. If the electrolyte is more dilute, the Debye length will be much larger, extending more into the solution, and then there will be a significant impact on of the proximity on the effective proton density. So this would be a factor 4, for instance, in activity. Hypothetically, if there could be, let's say, an oxygen reduction at these particles, a denser array of particles would lead to a 4 times enhancement of the activity. Okay, so that has a practical impact there. And so now I come to the last part of my presentation. I have about 10 minutes or 15? Okay, great. Okay, so now moving away from this kind of mixed quantum mechanical classical description to a purely classical theory of electron-ion correlations at interfaces. And this was developed by a PhD student, Niels Bohr. He just recently finished his PhD, and unfortunately, I couldn't convince him to continue working in academia because he was an outstanding student, as you will see, hopefully. So again, motivation, right? So capacitance. So the models of double-layer capacitance have been developed through many generations. The earliest was the Helmholtz model, then came Dewey-Chapman separately developing their approaches, but using similar physics and mathematics. And then Stern had this kind of ingenious idea to just combine the two and built this Dewey-Chapman-Stern theory of the electrochemical double layer, as you can see here. And so there's an expression for the total capacitance, or the inverse total capacitance is just the sum of the inverse Helmholtz and Dewey-Chapman capacitance. If it is assumed that the Helmholtz capacitance is just a constant, doesn't depend on concentration, Dewey-Chapman does depend on concentration, so it can be tuned, and there's the x-axis in this plot. And so based on this equation, then it should be expected that the relationship plotted of the inverse total capacitance as a function of the inverse Dewey-Chapman capacitance should be a straight line with a slope of 1. Okay, this is a prediction mathematically bulletproof of this Dewey-Chapman theory, right? Okay, so all in principle interfaces should exhibit this kind of behavior as long as this would remain constant, and the only, let's say, way of tuning this Dewey-Chapman capacitance would be a concentration effect, nothing else changing. Okay. Now, what is seen in experiment is a bit different. So here are different metallic systems, electrodes with mercury, with gold, and with platinum. And generally, it is seen that the slope departs from 1. Even for the mercury here, it's the closest to 1, but still there's a slight deviation. Gold, there's a significant deviation, so the slope is 0.2. And platinum is an extreme case where the slope is almost close to 0, right? And there is no theory that could explain this. There are various hypotheses. And for instance, it was discussed that there could be an electrode surface roughness, but this is platinum 111. This is the smoothest electrode that you could probably talk about. Okay, so that cannot be really the reason. Additional ion surface interactions has been speculated, but never, let's say, theoretically well supported. And a weak ion adsorption resulting in a pseudocapacitance has also been discussed. But none of these explanations is really, let's say, solidly grounded in theory. So it's all, let's say, there's an element of speculation in all of these. So what really is a unified explanation, or what could explain these variations between the theory and experiment in this Dewey-Chapman Stern limit? So why is there the departure in these Parsons-Sobels plot from the expected slope of 1? Okay, So that was the driving motivation for this part. And then Niels went about to develop a classical approach of electron-ion correlations at electrochemical interfaces. And so he developed a classical theory of Coulomb correlations. And how to treat electrons in a classical theory at an interface? Well, there's one approach that also has been pursued for many, many years, of course, and it's also, of course, an approach in classical textbooks of electrochemistry based on image charges, okay, as illustrated here. So here we have our solution environment, we have our ions in solution, we have our interface here, and ions can move around in the electrolyte, can get close to the surface, but what we introduced here was a distance of closest approach, a charge separation distance with a parameter A, and this will be in the range of angstroms or smaller even than angstroms. And then we also distinguish two regions on the electrolyte side. One, let's say a normal electrolyte region that has ions and has a bulk electrolyte dielectric constant, and a surface region that has an interface dielectric constant, which we can distinguish. And so the image charge model in principle corresponds to a limit of maximally correlated electron-ion pairs. We introduced this minimum charge distance. And so we consider the simplest model point ions and the dielectric background, and develop or obtain is targeted to develop a systematic extension of the Stern theory. Now, how to introduce the image charges is relatively straightforward. So we have a formulation for charge density, total charge density, the ionic charges and the image charges, and since the dielectric constant of the metal is infinity, so it's infinite, so this is the expression for the charge density. So point charges with the locations given here, and so we develop a statistical approach, so these charges could be found at any point in space, and energy is calculated for the different charge configurations. And then we, so the starting point will be a calculation or formulation of the classical partition function for the system, which has these charge-charge Coulomb interactions in the exponent here, because they give the different energies for different configurations, different distributions of charges. And then, and this was the main contribution that Niels made to perform a Hubbard-Stratonovich transformation. So away from explicitly considering particle-particle interaction to replacing these particle-particle interactions by interactions of a particle with a fluctuating local field. Yeah? And this is the essence of this Hubbard-Stratonovich transformation introduced more than 60 years ago. And so quite widely used in certain areas of statistical physics, for instance, polymer physics and so on. And then the partition function can be written not in terms of these particle-particle interactions, but in terms of an action functional that depends on this newly introduced field that our ionic species or charged species are interacting with. And this action functional then can be developed, and this is fully equivalent to this expression here. So mathematically, this expresses exactly the same with this action functional, the same partition function as we have.
I don't know what's the first.
Yeah.
That's okay, go ahead.
Yeah, please.
Quick question. So this is just a Hartree term, or so what you're having. Do you have also then some kind of self-interaction correction? Because at the moment your ions would interact with itself, or?
Yeah, they interact with themselves, yes.
Is this an issue? Or
that's not an issue, no.
Why? Because I'm thinking a bit, let's say, in electronic structure, and it's very similar, or? So you're missing then the...
First of all, it's a dilute limit. We consider a very dilute limit and weakly charged surfaces, so ion separations are quite large. And that's a prerequisite for this. I forgot to mention that, yeah.
And these are then the screened charges, or so what do you do then with your dielectric?
It's point charges. It's discrete point charges, yes.
Discrete, but are they screened by the Solvation shell?
They are screened, of course. There's a Solvation shell around it.
So it's 1 over epsilon r.
Solvation effects are included there, yes.
So, how do you get epsilon?
Epsilon? Oh, the dielectric constant. Well, that comes out of from the calculation. So the variation of epsilon
Yes.
with radius is a result of the calculation.
But what is the equation you use to get epsilon?
Okay, so so we could use, for instance, this statistical field theory that I was presenting earlier, right? So we get a expression similar to some of these that you have used, that you have shown, right? But then what we did here, okay, for the sake of, let's say, demonstrating capabilities of this, we just fixed the dielectric constant. We have one fixed value of dielectric constant in the bulk and one fixed value of the dielectric constant in this interface region, in this contact layer.
Although the dielectric constant is very far from being uniform.
That's right. That's right.
Okay.
So it's a simplified approach.
Okay.
A simplification. We'll see how that works, and of course, that would be an assumption to memorize and to relax later. Okay. So we get this, and so the advantage here is, so first of all, this, as I mentioned, fully exact expression, but it can be developed. So there is a settle point, so that corresponds to this field configuration psi 0. And so there's a systematic expansion, perturbative expansion that can be done around this settle point. And so first we take a look at what happens if you forget all of these corrections and just go to this point there. So in zeroth order, the electrostatic potential is recovered from let's say, a solution of this model, and from this condition of being at a minimum of this action, we then get the Poisson-Boltzmann equation out. Of course, this is totally expected, so this is just, let's say, a consistency check. And we also get the capacitance in the Gouy-Chapman form. So there's no, or in the Gouy-Chapman-Stern form, there's no correction for that. And so in principle, from, let's say, the configuration that we start with in zeroth order, we only consider uniform charge density distribution, no fluctuations or anything. So the discrete nature of the ionic charges is not doing anything at the interface. Okay? So this is the mean field limit. Homogeneous surface charge and the capacitance is the Gouy-Chapman limit. Now if we go to higher orders, because we are at an extremum of this action, so the first term should be 0, and the second order term has this correlation function in here. And now the terms contributing to the second order term, they can be expressed or represented diagrammatically with these Feynman diagrams. Okay, and this is, say, the mean field contribution, and the first clover has this kind of variation with this key parameter, which is this width of this interface layer. Okay, and there's then the second order term, and it turns out, so exact integrals corresponding to all of these different terms have been solved and then analyzed and plotted, and it turns out that only this contribution is significant, and it becomes very significant when this parameter A becomes very small, and other contributions of second order are negligible. And so now it's also possible to sum up all the terms. This series here is converging. So if you go to let's say, arbitrary order, the well, absolute limit can be calculated, and what we get out from this is an expression for the total capacitance, which is corrected by an interface correlation factor. So the infinite series converges, can be solved explicitly. All these integrals can be calculated analytically, or at least analytically expressed, and then we get this correction to the Gouy-Chapman-Stern capacitance. Okay? And this is a direct result of these electron-ion correlation effects. And the additional or this interface correlation factor depends on an interface surface ion interaction potential that is due to electron-ion correlations. And in most cases, as depicted here, this will be attractive, meaning that the correlation effect will lead to an enhancement of ions close to the interface. Yeah? Okay? And so now, of course, we can take a look. What will be the impact of this interface correlation factor on the capacitance? Okay? And due to the enhancement of ion densities, we would expect, let's say, that the Gouy-Chapman capacitance would increase because we have more ions in proximity to the electrode surface, right, due to these correlation effects. And so that we then was calculated, and the only parameter here, so here you see the dielectric constant used, okay, for the bulk and at the interface. And the only parameter that was varied was this this distance of approach of the ions to the interface, okay, or the width of this interface layer in the range of angstroms and getting smaller as we are moving from mercury to silver, gold, and platinum in different electrolytes. And you see here, with only this parameter varied, the experimental behavior in these Parsons-Sobels plots can be quite nicely reproduced. So the deviation from the slope of 1 and even the curvature for these different electrode configurations can be quite nicely reproduced. I'm almost done. So this theory, a fully classical theory of electron-ion correlations, suggests that these correlations are the origin of these decreased Parsons-Sobels plots. And the key parameter is this charge separation distance, so the width of this interfacial layer. And what is also interesting that you see the trend there for these different metals, mercury, silver, gold, platinum, and that basically follows the hydrophilicity of the different materials. Mercury is very hydrophobic, platinum of these is the most hydrophilic one, so the trend in this parameter A here seen follows this hydrophilicity. And then this was also done for different electrolytes. Now, of course, because we have different electrolytes, the dielectric constants must be different. And here we took, for the bulk values at least, experimental values of the dielectric constant. And also there's good agreement, and even, let's say, these peculiar effects in curvature could be reproduced with this approach. And so now to come to a conclusion. So this parameter A, this charge separation distance, is of key importance here. And what you see here is, well, this 1.8, you know, it's kind of a physically meaningful parameter. But if it gets very close to 0, it may not make a lot of sense. Right? So it's not really a physical separation. It's basically kind of a virtual parameter that expresses how, let's say, close ions can approach the surface. And what we see, and also it represents, so the closer, of course, the ions can come to the surface, the more delocalized, the more condensed will be the charge density distribution corresponding to the image charge here. If the two charges get very close, we will see a strongly localized Gaussian distribution here. If the distance is larger, like this 1.8 angstrom, it's more like a uniform distribution in the plane. Yeah? Okay? As represented by these image charges. And so, what it all, let's say, comes down to is kind of overcoming this mean field picture. And in the mean field picture, we have to distinguish electrostatic charging that results in double layer capacitance, in Gouy-Chapman type or Helmholtz, in Gouy-Chapman type capacitance. We have to distinguish that from ion adsorption. So they are considered as different, separate phenomena. What this theory of electron-ion correlation suggests is that these are just limits. Limits of the same correlation effect. And so this is an electron-ion correlation, and for platinum we had this case here, basically maximum condensation of ionic charge at the interface, electronic charge and the ionic charge actually merge. So this corresponds to ion adsorption. whereas in other cases the distance is larger, so this would be the pure electrostatic charging. And as a function of this parameter A, there's a continuous transition from the electrostatic charging to ion adsorption. So it's kind of a conceptual unification of double layer charging and the coupled electron-ion transfer. And that's where we are at the moment. I know there's a lot of, let's say, physics to talk about and assumptions that go into it. But I find it interesting that a purely classical approach, first of all, it can reproduce these Parsons-Soboles plots quite well. And it also gives us a very interesting kind of perspective on phenomena that we usually consider as separate, but maybe they are just the same phenomenon considered in different limits. And so with that, I'm at the end, and thank you for your attention.